So, hello everyone. I got brand new batteries, so you should hear me well, I hope. And again, we are changing topic, and I will be talking about population synthesis now. And I think there are quite a few people here in the room who may know more than I do, so I will divert any questions to those people, in particular Jan sitting there in the back. I can say this already now. Okay. Anyhow, let's start. And before I go into the real topic, I would like to go back to the lecture today in the morning and pick up a few topics that were asked for one thing, and then go later on to the population synthesis. Okay, gap and migration, that was the topic today. And there's a classic paper by Doug Lynn and John Papaloizou from 1986, which was well before all these exoplanets were discovered. And they did a simulation here on the right. You see, I didn't label this in this way. I will come to the paper on the next page in more detail. So here, for different parameters that I can't recall now, you see gap formation in these disks created by Jupiter-type planets. So it looks very similar to what we see in 2-day simulations, in fact, as well. And this is migration now for different parameter here. Time goes from here to here. Okay. This is radius for Jupiter-type planets here and different parameter. And interestingly enough, this planet moves out, okay, in those days. I was surprised to see this also in the comparison. We think planets move inwards, and they found planets move outwards. Okay, we can look into this in more detail. This is the paper on the tidal interaction between protoplanets and the protoplanetary nebula, paper 3 already, orbital migration of protoplanets. Doug Lynn, John. From the above results, we make the following conjectures. Jupiter was formed outside the present radius of Mars, okay. And second, the disk mass exterior to Jupiter's orbit at formation did not exceed that interior to its orbit by more than 0.1 solar mass. Otherwise, Jupiter's orbit would have evolved into the protosun in less than 10 to the 6 years. Okay, this is all correct. They didn't want Jupiter to move inward because they thought, okay, Jupiter is there where it is, which is fine. But shortly afterwards, we discovered, or not we, shortly afterwards, in fact 25 years ago, yes, or 20 years ago, yeah, 1995, 20 years ago. 20 years ago, the first exosolar planets immediately showed that we do have many hot Jupiters very close to the star. So this was, in fact, they got all the results here correctly, basically, and they placed the planet in the outer parts of the disk, so there was not much mass beyond the radius of Jupiter. And then the viscous disk was expanding outwards, and that's why this planet was moving outwards. And that's why this discussion about the mass is in here. So, but we know the disks are much bigger from the observations now, as we have heard today and the other day. And so we know there is lots of mass outside there, and the outer disk, as we know, as we have heard, will push the planet inwards, and Jupiter would like to migrate inward. Okay, so this was 86, and then after the discovery of 55 PEG, immediately Doug Lynn and others wrote a paper explaining this by a standard migration process. Okay, then there was a question about accretion onto planets. This, I repeat this here a little bit. So we have here a growing protoplanet, Jupiter mass at 5 AU. So, and this is the Roche lobe of the planet. Okay, here's the L1 point, here's the sun somewhere. So these are the streamlines of particles in the co-rotating frame with Jupiter here. So we can see we have this circulating particles outside, circulating particles inside, and particles in this horseshoe region here. Yes, and we can see particles which come here, can enter the Roche lobe and be accreted potentially here through a circumplanetary disk onto the planet. The question is only how fast these accretion through this circumplanetary disk can actually occur. This is not really a resolved issue now. There are several simulations now coming up which try to resolve this central area in much more detail. Okay. with special numerical methods, this is nowadays possible. So we need to know how much mass this planet can actually accrete. And as you can see, this is for one Jupiter mass planet. There is a gap here. This is low density. The red is high density here. So even then the planet can accrete. And formally, planets can accrete to masses of around 5 Jupiter masses. And for larger mass, then the disk becomes eccentric and so on. And then for eccentric disk, you may reach even higher planet masses, but this is beyond, I think, the talk now. Okay, so we can see through these streams of material that enter into the rush lobe, the planet can accrete beyond gap formation, basically. Then there was something about eccentricity and inclination. I had to skip this today in the morning, and I will show you here an example of a planet with 0.1 eccentricity in a disk. Okay. Looks like this. So we see here these spiral arms that are created by the planet are changing periodically. So they are strongly time variant here. So if you want to calculate the mean change or the change of the orbital elements, you have to integrate over one orbit and to average this over one orbit, because sometimes you have positive torques. Now you have negative torques, positive torques, negative torques. So you have a strong variation of the torques, and they change sign within one orbit regularly. So you need to calculate this very carefully, and then you can integrate it and estimate the change in eccentricity the planet experience on average. Okay? This is the option with hydrodynamics, and then there is also linear analysis, and both lead basically. For small eccentricities, you get an exponential damping of eccentricity. Okay, for large eccentricity, it follows this relationship here, which is slightly weaker. Yes, and the time scales for this exponential damping of the order h over r squared, which is a small quantity, times the migration time scale for type 1. For, as I was saying, this is I think, 20 Earth mass planet here, so it's a relatively small planet. So this is the time scale for eccentricity damping. As you can see, this is small. This is much faster than migration time scale. So we can assume, you can safely assume that these planets that are formed in disks and try to move around, that they are on circular orbits with 0 inclination. Okay. So planets tend to settle to the disk midplane on relatively fast timescales. Okay, that were the additions. And now I come to the real topic here about population synthesis. Okay, this I think is a very difficult word for me, being a German guy. Okay. So, distribution of planets. This whole topic is about explaining the statistical distribution of planets. This is different to some other approaches here. Here try to find solution explaining this whole distribution here in this crucial diagram, the planet mass versus separation here for these different planets. You try to find out why you have more planets here, more here, or less here, or something like this, or maybe less in between here, more here again, and so on. So this is the goal of population synthesis. You produce many, many models, vary certain parameters, and then you try to fit them to this observed distribution here and try to figure out which parameter is crucial for determining the statistical outcome of planets. Okay? So it's very clear that this is not a uniform distribution here. Okay. And these are all planets where the mass has been measured. Okay, this is, for that reason, it does not contain too many Kepler planets. For Kepler planets, we would need to draw a different diagram. We would need to plot the radius of the planet here, and here the separation or the distance from the star. So this is a very recent plotting, in fact. And then there are other correlations. I just mentioned a few ones here without going into details. I think these are the last ones I will show. So quite a few years already, it is known that stars which have higher metal content, which is measured by this index Fe, iron over hydrogen, with respect to the sun. So 0 means this is the iron content of the sun. This is less iron, so these are metal poor stars. Positive here means those are metal-rich stars, and metals is everything beyond hydrogen, as you know. Okay, beyond helium. Sorry, beyond helium, everything is metals here. Yeah, so you know, and then it is known, this is the relative frequency of planet occurrence in stars with this metallicity here, and this is basically for high mass planets, so Jupiter-type planets, okay? And this was the first relation that was discovered, because with the AV detection, this was primarily high mass planets were detected. So you can clearly see the higher the metal content of the star, the more planets such stars will on average have. Okay. On the right, this is the interesting, more recent discovery. These are the low-mass planets. Okay, these are planets with a radius smaller than 4 our Earth, and they have this blue distribution here, and these ones here are for larger than 4 Earth. And here, honestly, I don't see much difference here between the red. I don't know whether this is significant, whether the red and blue distribution are really the same, or are they different. Yeah. Statistically, I don't know. There seems to be a slight trend that this is more moved to the right. But obviously, here the numbers are higher in the blue distribution here. Lower mass planets do not show this strong correlation here with stellar metallicity here. Okay. Good, and this is summarized in this picture here by Greg Loughlin. Okay. So, as I said, the motivation for population synthesis is we have thousands of exoplanets observed, nearly 2,000 at the present time, and it is not possible to model each of these systems individually. Yes, of course, for some very special cases, you think, wow, this is incredible. We have a planet here with 20 Earth or 80 Earth mass core or something like this, so people try to model this, of course, separately from the others. Yes, but on average, you get a whole distribution here of planets, and you cannot observe, let's say, cannot find models for these individual systems. It's, as we know in the solar system, when we try to explain the solar system, there are so many details known, and there are so many parameters you can tweak and play with to explain the solar system. And to do this for a single base study for these exosolar planetary systems, so this would be way too much detail you need to know for these planets. Okay, so we observe explanation for the statistical distribution, as I said, for example, in these diagrams here, which are very important here, and try to get some explanation for these structures that you can notice here. And this is a statistical approach, as I said, by definition here. So you combine disk evolution models with planet growth and dynamical evolution. So you model the disk and the planet simultaneously at the same time. So the disk evolves in time, as we have heard now, viscous evolution of the disk, and then it evaporates and so on. And at the same time, the dust in these disks coagulate to planets, form cores and so on. And you try to model this with some limitations in time together. And of course, the limitations, you start already out with some grown, let's say, population of bodies there, which are big enough, so then you can continue from there. You vary the parameters there. Yes, I will talk about some of the parameters here and calculate the statistical outcome and compare it to the observed distribution. And then you identify, this is very important, and there are a few points which I would like to point out here. You try to identify the crucial parameter that determine this type of distribution here. And the outcome is sensitive to some parameters, or more sensitive to some parameters than to others. And it would be the goal to find those parameters where the outcome is very sensitive, dependent on. Okay, this is pioneered here by Shigeru Ida, Doug Lin, and at the same time by Jan and Willy Benz and Christoph Modassini from Bern. So this would be this sort of Bern group, and this is sort of the others. Yes, in this room I can say this, yeah, okay. And there are many subsequent papers primarily by these two groups, yes. Okay, methods. Yeah, long list of methods here. I will not go through them in all glory and detail here. Initial conditions of these protoplanets, they are a fraction of an Earth mass here. We have a gas surface density of the disk. We have a dust surface density distribution of the disk. So not only minimum mass solar nebula, but you can vary this a little bit. You can play around with the exponents and so on, with the ice line and the dust fraction here, and so on and so on. The planet growth and orbit evolution, you model this basically in the same fashion that we have seen in the last few days here. Runaway oligarchic growth, post-oligarchic accretion, gas accretion onto planets, massive planets, dust accretion onto planets, migration, type 1 and type 2, viscous disk evolution, disk dissipation, and so on. So basically, you take everything that you heard in the last few days, put it into a pot, stir it a lot, and let it bubble to 100 degrees, cool down again, and then you try to eat it. That's how it works. Somehow. Then you try to find something out, what has happened here, and get compared to the observations. So the sigma dust is a fraction of the gas density here typically, and then you have some ice also beyond the ice line. This is also included here, of course, and the dust is a fraction of the gas here times the metallicity here. So the metallicity, you can also play around with that for the star. And then you have Monte Carlo methods. You vary the initial conditions of the planets. You change, for example, the dissipation timescale, or you change the fall off, the exponent of the density fall off, and so on. And you vary this around a value which you believe you have obtained from the observations. So we have just seen in the talk by Leonardo here that you think the disks have a certain density, typical density fall of sigma of r. In the inner parts, it's a power law. And then when you go to the outer parts, you have an exponential drop-off here. And you plug this in and vary this a little bit and run many different models with slightly different parameters. So you can see what difference it makes whether I have, for example, sigma gas r to the minus 3/2 or sigma gas r to the minus 1 or r to the minus 2. And you can then see what the outcome is, can see how sensitive the outcome is on that parameter sigma of r. You correct me if I say anything wrong, Jan, okay? Or otherwise, I'm getting out of bounds here. Okay, so input parameter, for example, planet growth. This is the planetary growth is modeled as part of this synthesis modeling here. You need to model for each planet in time while the disk evolves. You need consistently to accrete material, move the planet, accrete again, move it, and so on and so on. So you need to know how long it takes to accrete this material here. And these are just two examples here from Pollack et al., which Jan provided here. So we here have the different surface densities of the solids here, and you can see here the evolution time is about 30 million years, and here it's only 8 million years. So this varies a lot, the evolution time of the planet. We have seen this already yesterday, and you put this into a model. So you vary the abundance of the solids, and then you, of course, the planet take longer to grow, and the evolution time of the disk is also a little bit different then. And then you can see whether you can make planets if you have these low surface density of dust. Can you really make enough planets in disks which are big enough, let's say 50 AU or something? Okay. So 33% in solids here, a factor of 4 in time scale. So some parameters, as you can see it here already, have lots of influence. Good. This figure I didn't show yesterday when I was talking about the planet evolution here. So when you have here the time running, there's the radius of the planet. For example, this would be the total radius of the planet of the Jupiter here, Proto-Jupiter here. It first increases here, and then suddenly it condenses here when you have rapid accretion here onto the envelope here. So it condenses very rapidly here. And here's for the luminosity runaway accretion of the envelope leads to large luminosity spike, and this gives rise to the potential possibility to observe those planets here. You have a sudden increase in luminosity by several orders of magnitude of this protoplanet here. And this, of course, is the goal by some methods that Leonardo pointed out here to observe a planet in this phase. But you see the phase is short. Okay, you have to be lucky to capture a planet in this short phase, runaway phase, where it's very bright. Okay. And then it cools off here, so this is 10 to the 10 years or something like this, yeah. And these curves, you have, of course, different models that go in here, starting from Pollack in 97. Yeah, there's a consistent improvement also by Christoph done in the last years and by others, and also by other groups here, Burroughs and Baraf. And then you can compare your model to those models and check whether they are different or not, and whether you have at least an agreement in how planets grow in disks here. The disk structure, of course, there are different approximations possible. Power law distribution here for the temperature and for the gas disk here. Then you have a fall off, only look at these few equations here. Then you have a fall off in time. Yes, the disk is slowly dissipating due to external sources. It's photo-evaporated basically by stars which may be outside of the disk. So they have an outside evaporation, you have an inside evaporation from the star the disk is surrounding, yes, from the host star, and those lead on average to a dissipation of the disk and to a reduction in the density here. So this is the correction factor here, so you can see this declines in time. This is the approach, I think, of Ida and Lin here. So you just have an exponential decline of the disk density, yeah, with a certain dissipation timescale, which you can vary then from, let's say, 1 million year to 10 million years and so on. Okay. Or you solve for the viscous evolution of the disk. I will show this on the next slide. Vertically, we have seen the vertical equilibrium equations. I think Phil has shown them today. You can integrate them. The disk has a finite thickness. You can integrate it vertically and get the local structure of the disk, from which you can then calculate also the viscosity, because the viscosity depends, as we have seen, on the temperature in the disk, and the temperature in the disk you can only know if you do consistent vertical models and calculate what amount of energy is locally emitted from the disk. Phil has shown this in more detail. Okay, so you need to calculate the vertical structure as well. As you can see, there's many different things that go in here, very many different things. For me, too many, too complicated, okay? Anyhow, this is the disk evolution here. This is the equation, I think, that Phil has shown, the regular diffusion equation for the surface density sigma. It's the diffusion equation because you have twice the radial derivative here and once the time derivative, and this we call diffusion equation. So, and then you have additional terms on the right-hand side, okay? This is envelope accretion. So there's still some material falling in the earliest phases of the disk, some material falling down on it, probably spread out with radius somehow, I guess, yeah? So you have a radially dependent accretion rate from the envelope. Then you have evaporation in time, which is shown here, by the way. This is the initial distribution here of such a disk, and this is how it evolves in time, downwards here. And this indentation is not caused by a planet, but I think it's because of evaporation, yes. Evaporation here, which comes from the inside, and here's evaporation from the outside. Okay, this is basically this term here. You model this by some, let's say, analytic formula you get from other people. And then you have the accretion of gas onto the planet, which you have to take out, of course, of this local surface density. So you evolve this equation in time simultaneously while you grow the planets and move them. Okay? And as you can see, there are many different things going in here. I don't know which parameter is most important in this modeling, but I think it's very nice what one can do. Okay, and then one does planet migration, and this was a plot I haven't shown yet, that's why I show it now. Planet migration has become more complicated due to this type 1 business here, which is a crucial ingredient. That's why I have to repeat this here again. This is a plot by Bitch and others. This is the planet mass in Earth masses here, and this is the radial distance here, and plotted in colors here is the torque gamma, the torque strength as a function of these two parameters here. And you can see sometimes they are positive, this is this reddish bit here, and sometimes they are negative, this is this more bluish bit, okay? And within this solid line here, the torques are positive, and outside they are negative. So here they're positive, and here again, negative here, yeah, negative here, positive here. That means, for example, if a planet is here and has this mass here, it will move out until it hits, if it doesn't grow, until it hits this line, and there it will stop because the torque is 0. This is a so-called zero torque radius. And the planet here with the same mass comes in here because it has a negative torque, and they will meet at this zero torque radius. Okay, so this is a collection point, which changes, of course, the evolution of a whole planetary system. If you happen to have more planets in there, they can collect there and then do something strange. Okay. And the same, if they grow, for example, you start out here and the planet grows at the same, it moves outward and then it hits the point at this line here, okay? Then it can already meet a planet coming from the outside here. Or if it grows directly here, then there's only inward migration possible. So above a certain mass here is inward migration possible. And you can see this is quite a bit smaller mass than I have quoted today in the morning, which was around 20 or 40 even. Yes, because this model is more advanced. So here there's stellar radiation invoked here in this model. So this is a little bit more elaborate here. And this is the ice line, by the way. This is also included in this plot here. So the recent models, population synthesis models, include this type of migration business that is contained in such plots. Okay. Good. Yeah, and this is the procedure, how it works. Yes, Jan? Sorry that I have to ask you all the time. I just think that's the best way. This is from the review by Willy Benz and others from PP6, where you can find everything in detail. So everything I have told you is contained in all of these models. So you have the vertical structure of the disk, the radial disk structure, the solids in the disk here, and then they have the atmosphere here of the planet, the envelope, infalling material, core structure, migration, planet-planet interaction. This is a new module here. If you have more than one planet, they can dynamically interact here. This is this model, module 10, accretion rates, and there's lots of interaction errors here between these different models. So each model contains a whole bunch of physics that I have talked in these lectures. So this was today's morning lecture here. This was the growth of the planet here one day before, and so on. Yeah? So this is very complicated business, and there's lots of work to do for these individual modules and then put them together in a proper way. I think I don't need to explain anything more here. You can easily imagine that you need basically all the physics about planet formation is contained here. Okay. So what are the results then? After I've explained the methods in great detail, yeah, I could take the famous 5-minute discussion round right now, I think. Just look at the time. So, it's time to continue. Okay, the results. I hope I get through all of them. If not, I will just speed up, as usual. So, no, doesn't work. So, the classic diagram by, I think, Shigeru and Dag is the following. Here you have the synthetic diagram, the mass and distance relation here that these models produced. Okay, so you have some gas giants here, Jupiter masses, and then you have some hot Jupiters, many hot Jupiters here piling up. You can't really say how many are there. There are very many. You have a planet desert, you have icy planets and terrestrial planets. So in principle, all the later diagrams look similar. Yeah? So I could stop here and say nothing more, but there are, of course, the details which are important here. Okay? Too many of Jupiters and so on. So there's no type 1 migration, even in this one here, only type 2 here. This is solar metallicity. The planet desert here it can be explained basically because you have little gas accretion for planets which have too low mass here. Only above this you have a runaway. So basically you have many planets which didn't make it to the runaway phase because this may take a long time. And then suddenly the runaway begins and you jump immediately from this mass to that mass basically. So this would explain quite naturally this planet desert. And later models find this in fact also. So this is a generic feature after all of these models. And also somewhat I will compare this later on to the observations here. Okay. And then you have very rapid inward migration here, too many hot Jupiters. These are the very first results. And they have more ice here, it's clear. At the outer radii you have more ice, and the inner parts have more solids. I mean, it's rocks, basically, yeah, like the terrestrial planets. So this is the classic diagram here. Then you can see I will skip this diagram here. So then you can check the influence on type 1 migration. This is a crucial point. I've talked about this in the morning. And there's a correction factor that some models here applied. The migration timescale is C1 times the classic migration timescale, classic type 1 migration timescale, which was always inward, if you remember correctly. Okay? And this factor C1 could correct this type 1 migration timescale. So here you have basically, yes, C1 equal to, what is this here? Okay, to different values, 0.01, let's start here, 0.1 or 0 here. You can see if you need a small reduction factor here for C1 to get, let's say, not to get too many hot Jupiters here. Only with a strongly reduced type 1 migration you get agreement here for these planets which are out here. Yes, you see, that's what you want to match. You want to match these planets out here. If you have large type 1 migration, you don't get any more planets here. They all move inside. Okay, when you lower it, you get suddenly lots of planets out here which are observed. Okay, so to reduce the number of hot Jupiters that are produced and to keep those planets out here, you need a strong reduction of type 1 migration. Okay, that's the whole point. So this one here only factors 100 times slower than the classic type 1. This gives roughly the agreement here. Okay. So from that you could learn, which is I think a very important ingredient here, that the typical standard theory of planet migration could not be the correct one. Then you would lose all the planets into the sun. Okay. The next one is influence of type 2 migration. Very briefly only here, there are two different approaches, slightly different prescription for the planet type 2 migration here. And this is the Bern group here, which gives too few hot Jupiters here. And the Ida group here gives too many hot Jupiters here. Okay, so this is I don't go into the details how this description is done, but they don't seem to be too different. Yeah? So it's anyhow, okay, the details is in the PP6 review by Willy Benz and others here very recently. Okay, so this is a slightly different treatment of type 2, leads to quite different results in the outcomes. So this is in fact also interesting and important here, that you have two different approaches. So you can always compare two independent codes, two independent inputs, two independent, let's say, little modeling features. So you can always compare between these two models also, and then you can identify the importance of these parameters here. Okay. Then you have the dependence on metallicity here. It's very clear. It seems to be clear that the more metals you have, the more planets you can form, because you have more solids in the disk available. If you have more solids, you can easier form the cores of the planets that you need to accrete later on the gaseous envelope on. Yeah? So you have more solids, you can produce more planets, of course, and get to higher planetary masses also. This is measured by this parameter delta Z here. Yes, if this is very high here, yeah, you have many more planets here. Yes, and you can then vary this individual. Only this parameter is then varied, and you can see when you get the best match with the observations here. Okay. Then this is the convergence zone. I will also skip this here. This is a sample outcome of one of these simulations here. Also from this, it's also mentioned in the PP6 paper, I think. It's from Ida et al. 2013 here. You have here a system of planets. This is the new development of the last few years. You can add a few planets and they interact with each other. And they can excite eccentricity. Yes, they can have certain non-zero eccentricity here, and you have dynamic interactions between them. They can get into resonant configurations and so on. Okay, and here they use a statistical approach to model these multi-planet systems here, while the Bern group is using direct modeling, also n-body modeling, and even hydrodynamic modeling here. Okay, so you have the time here, and here you have the different, the distance here, and so you see how the planets, if they grow initially, then they begin to migrate inwards here. There's some collision behavior here. They grow, and a few planets make it to 10 to the 9 years here. And this is the final outcome here. The final outcome is shown on the right, and on the left you have the time evolution. Basically, you can see you make a system of super Earths here, and then you have a sort of giant here and some ice planets further out. So this is only one case study here. So this is not to be generic here. Then you vary some parameters and produce many of those cases. And then you plot them in this diagram. So this was only a sample simulation here, how this looks like for one system here. If you want to model the solar system, for example, and compare it directly here, then you would do this exactly, try to match this exactly with the parameters of the solar system here. Okay, this is a nice animation by Christoph Moracini here, where he shows the evolution here with a little movie here, okay? So you can see this here. Planets begin here at the bottom here, yeah, and then they grow first, and then suddenly they begin the type 1 migration, and then they have here change to type 1 outward here, until later if they grow more in masses, they move in again. So you have different possibilities of the migration of planets, okay? And these is not a multi-planet system. These are several realizations, statistical realizations of individual single planets just plotted in one movie here, okay? So this is all single planet evolution, yeah, and you can see where they end up here, yeah, in time here. The time is running here, 1.5 mega years here. So this is here classic gaseous planets here on their type 2 migration trip here. This is red is outward migration here, and bluish, I think, seems to be type 1-ish migration, okay? Oops, so they still go. I mean, we need to cover 10 million years, okay, but I will shorten it for you. Okay. Okay, so this is what you can do. You can look at the whole ensemble here, and these are the colors for the animation here. Locally isothermal, inward migration, adiabatic, unsaturated, so you can have outward migration, adiabatic, saturated, and so on. So these are the different migration regimes you are in, classified here by Christoph Moracini. Then type 2 migration. We could see this in the diagram that changed the colors of the curves when you enter different migration regimes. And as I've told you today, these different regimes of migration can be calculated from the local disk structure, which you model simultaneously. You see the disk evolves also. Then you look where the planet is. You see the structure there. You have the viscosity, temperature, density there. Then you decide, okay, now it's under type 2 migration, and then it moves under type 2, or it's under type 1 migration, outward or inward. So we decide this on a local basis. Yeah. Okay, and that has, of course, reduced the problem of too rapid type 1 migration. Automatically, you get a strong reduction of C1 here just by adding more physics. So these results showed immediately that there was a problem with type 1 migration. And that's why population synthesis is so important. So you can identify those parameters that play a very important role. Okay, and that told these comparisons with the observations told us theorists directly, okay, here you need to do more work, yes, and we believe we have done part of the work here in identifying the crucial parameters that determine type 1 migration and even could have it moving outward in between. And that, of course, saved many planets from falling into the star. Okay. Second, which is a very important outcome of these simulations, is the so-called planetary IMF, the planetary initial mass function. For stars, this is of course well known. Yes, there's the stellar initial mass function, Salpeter and others, since 50 years and more. Okay, so this is basically the number of stars here, number of planets per mass bin. Okay, how many solar mass stars are there in comparison to 2 solar mass stars, or are there in comparison to 1/3 solar mass stars? So here, the question is, when we have reached the endpoint of the evolution after 2 gigayears, let's say, there's no more gas disk available, the planetary system does not evolve anymore, then we look at the mass distribution of these planets statistically and compare this to the observed mass distribution here. Okay, so here we have this here, and what we see here is superimposed of the simulations. Here we have the observations here, yes, and the crucial point is that you have in both the observed distribution and the synthetic distribution here, you have basically a little bump here in the Jupiter type of mass range here. This, I think, here is Jupiter would be here. 300 Earth masses is Jupiter. This is higher mass, lower mass here. And then you have a little valley here, and the observations not quite as clear. And then you increase strongly towards lower masses here. It's just similar with stars. There are many more stars with low mass than there are stars with high mass. There are many more asteroids with small mass than there are with high mass, and so on. So this is a generic feature. This here is very generic here at the end, of course. Yeah, but here the dip here is after all a consequence of this core accretion model. So if you look at this here, so this can be a proof essentially if these planets are formed by core accretion or not. Yes, because core accretion tells you we first make the cores, and this cores hover around because they have reached the isolation mass, they hover around whatever 10 Earth masses and so on, and then suddenly you get the mass increase to the giant, so suddenly you move out from this region, blip, to the giant phase, or you remain small. Okay, so you have some expectation here for this. So this could be in some way showing you something about the formation scenario of planets. Okay, and this is reasonably well, I think, here fitted. And the reason for this, as I said, for this valley is core accretion model. I don't know whether I wrote it down here. Imprint of core accretion model. Okay. Next result: mass-radius relation. This is a quantity that you can observe for transiting planets where you have in addition radial velocity data. So the transits give you the radius of the planet. At least it gives you the radius of the planet in terms of the stellar radius. So when you know the stellar radius, or you believe you know the stellar radius, then you know the planet radius. Okay, that's the way how it goes. And then in addition to know the mass, you need in addition radial velocity data. You need dynamical data for the star, and this unfortunately cannot be made for the Kepler systems. This is really the major drawback, if there is a drawback for the Kepler mission, that we cannot get radial velocity data. Okay, so we do not know the mass of the planets. Okay, but if you happen to know the mass of the planets, you can plot it here, and you can plot the radius of the planets, and then you plot the observations here, blah, 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 okay? These are Kepler, Uranus is here, Kepler 10, Kepler 11, yeah, and some other planets. And these ones here, the colored points, are the endpoints of synthetic planetary evolutions as done by Christoph and others a few years ago. Okay, so and the colors mean different metal contents. I don't know whether you can read this. This is Z smaller than 1. Then it goes up here, 99%. I think this is in terms of solar metallicity. Is that correct? I can't remember really. Okay, you vary the metal content whatsoever here of these planets here, and you can see here different types of endpoints here. So you can say, okay, if we have a planet here, it has a Z fraction of 5 to 20% of the planet. The mass of solids in the planet, exactly. It's the percent, yes, the percentage of solids in the planet. Okay, sorry. It's not the star we're talking about here. I'm getting confused myself sometimes. Okay, this is the amount of solids in comparison to the total mass of the star. So 99% means it's only solids. Yeah. So this is down here. Yeah. So we have planets here like Uranus and others which are only solids. So some of the Kepler systems are very, very solid without a little an envelope here, and down here you have large envelopes of the planets. Okay. And then you can see that if you do this, you can then compare the number of solids with the that you have at some location with the observed planet here, and can try to infer what the major constituents of the planet will be. Whether the planets are solid down here or whether the planets are more gaseous up here. And some planets, of course, stick out here. Yeah, this is, I have another, in one of the previous lectures, I think, was it today in the morning, or yesterday's lecture, even I think yesterday's lecture, there were a few additional slides that I couldn't show, which give this mass-radius relation. Okay, there you can look it up, and then you can see that you have lots of planets which have a radius which is larger that you can actually achieve even if you have a planet with only hydrogen. Okay, these are planets with only hydrogen, so this planet is bigger than a planet with only hydrogen. So the question is, how can you make that? Okay, how can you make a planet with a density that is lower than hydrogen or something? Okay, good. And this is now the metallicity distribution here of the observed planets here. And this is the number of planets around stars with a given metallicity. This was the diagram I've shown you in the beginning here. And you can do this for planets of different masses here, and for one distribution here, this I think is here the black line here. These are systems with gas giants here, and they have a slight offset to higher metallicities here. It's not so easy to see, yes, but this black dashed line here is the high mass with the giants in there, and there you only get these giants if you are slightly offset here from larger metallicity. But the relation is not as clear as the observations seem to tell us, and you don't have this offset here for planets which only are in the small mass range here. Okay, so you try also to fit this relationship that you have more massive planets in stars which have a higher metal to hydrogen ratio here. So this is this diagram. You go through these observed diagrams and try to find good matching points here. Yeah, this is a diagram where you compare the number of planets that you have with a certain radius here to the Kepler data. Kepler measures the radii, and from the population synthesis you know what the planet is made of, because you know how much gas it has accreted, you know the amount of solids it has accreted, so you know the constituents basically of these planets. You can make a hydrostatic model, and you know the radius of those planets, of course. Yeah? So the internal structure of these planets is again modeled simultaneously with the evolution, of course. Yeah? So you know all the radii here. And this is the red one is the synthetic distribution, and the blue one here is the observed distribution. It agrees very well in the outer parts here. Here there are some problems here. I can comment on this here, and this was a very similar diagram here. So you can see here for planets larger than 2 Earth radii, very good agreement here. For planets smaller than 2 Earth radii, not such a good agreement. And according to this paper here, it seems to be that the difference may be in the model atmospheres that have been used here, which contain in the models only hydrogen and helium. And these are only the lightweight molecules here, or atoms here, and they enhance, of course, the radius of the planet. So if you were to take more solid, or more, let's say, higher elements into the atmosphere, then you would reduce the radius of the planet here. Okay, so this may be a difference in the atmospheric abundances here you have. Okay, so even there you can see if it matches very well, you think, okay, fine, we have found the solution here. But if you have something which doesn't match, then you try to find out why it doesn't match, and you try to identify that parameter that can potentially change this mismatch here. Yes. But as we have just discussed here with Jan and Stefan here, that it's also important to identify those parameters that do not make any difference. Okay, those you can just throw aside, yeah, and concentrate on the other ones which you think make an important difference in the distribution. Okay, summary of this. Yes, as I've said, it's important to single out important parameter and those which are not so relevant. Okay. Important is the metallicity here, determines the time scales, of course, abundances of planets, planet masses. We have seen this. The metallicity changes the mass of the planets. Migration processes, we have seen that through these population synthesis models, it was possible to identify problems with type 1 migration, for example, which later on was seen to be a real physical, let's say, inaccuracy we had initially. So later on we knew, okay, we can do better, and this was shown, pointed out by these population synthesis models, okay? Multi-body effects here, they are newly implemented in different ways. This is also very nice that you have two different approaches, that you implement this by direct modeling or by statistical modeling. This gives you the possibility to compare two different approaches and see whether they give different results or not, and which one matches potentially better the observations and not. And the last point, which is now increasingly becoming more important, is the physical characterization of planets. In the mass radius diagram, you want to know what materials are the planets made of here that we see, and this can be done, as I've shown, through this population synthesis diagram, and more later on, you want to know the atmospheric composition, because the planet evolves in the disk and accretes material from the local ambient disk, and if you believe the disk at a certain radius has such and such composition, then you can get a composition in the atmosphere of the planet that potentially can be observed in the future. And the idea is you observe certain materials in the atmospheres of the planet, you can say where and how they are formed. This is, of course, the idea for the future. Physical characterization of the planets here and the planetary atmospheres in particular also. Okay, and that's basically what I wanted to say.
Thank you. Just a question, just to remind you, this is already out since a few weeks. That was a competition by Amaury usually. So.
Okay, good. Since a few weeks. Yeah, I will repeat the question anyhow. Mm-hmm. Far away. No, I will talk about this tomorrow, in fact. This was a very good question. So the question was basically, if we look at the distribution of orbital elements, we have many planets that are on eccentric orbits, and we have in particular planets which are in oblique orbits here. And the question is, how can population synthesis models explain these type of orbits here? And at the present state, I think inclinations are not included here because this would add another parameter, even though with n-body potentially you could do this. But I think the idea is how you produce these inclined planets is not quite clear how they're actually made. And I think before we don't know this, yes, it's hard to do these population synthesis models for those planets here. But people are doing this. People assume there are different formation scenarios of those systems here, and that they try to find, let's say, statistically the outcome of possibly different models. And I will talk about this tomorrow, in fact, how you can make inclined planets, because I've just said a few minutes ago that planets are preferentially on circular orbits in one plane. So the question is, why do we observe so many eccentric planets, and why do we observe so many inclined planets? Yes?
Just to comment, n-body is really, so there is inclination like big
Yes.
Down.
Yes.
In the mass release diagram you showed the solids you talked about. What is the composition of those solids? Are they just like silicates or something which is used usually, or?
I don't know. Maybe the solids have solar composition, and then you just add them up. Jan? I don't know. This is a detail of the population synthesis models.
You cannot see on the diagram, it depends where the planet was formed. So inside it's silicate iron, outside it's silicate iron and volatiles. So but Z is just a mass.
Does it also consider volatiles like carbon or something?
Yes. Yes. This is included, but I don't have a number for this one. But I'm not sure.
So it was a difficult question, apparently. Okay, but you can make. I mean, there are several. I think yesterday in the talk when I talked about the Jupiters and so on, I have a diagram there, mass radius diagram with observed planets, and then with synthetic models which only contain iron, for example. So you can see where a planet which only had iron would be located at. Or you can produce planets that only have carbon. You can make carbon planets. You know, this famous diamond planet that people have discovered because it was lying exactly on the 100% carbon line, you know, and things like this. But then you need to know exactly what the composition of the material is. So I could only estimate here that you must have something like solar composition within these metals here. You know, the metals must be solar distributed. I don't really know. And then you know, if you assume a solar composition there, then you know, when you know the number of Z here, you know exactly how much iron and how much silicon it has. That's what I assume. It must be solar type, oh, no? Okay. Sorry, is there? Okay, the question was, is there any problem in disk evolution models? I can just repeat what Jan said, there's no problem. No, I mean, it's of course there's a problem. There are big problems. We have heard this today and yesterday by Phil. I mean, the point is to have a disk evolution model. You need to know how fast the disk moves inward. I've shown you the relevant equation here, okay? The relevant equation, it's very crucial. Is the evolution equation for this disk here, okay? And you can see already that there's a big problem. In fact, by this red quantity here, okay? You can see this is just written like this. But we don't know several things there. Yes, as we have seen, this quantity alpha, the disk viscosity, is basically not known. Okay, this is the problem. Okay. This is a short summary of the problem. This is my answer, then Jan's answer is yes, it's known. So it's and Phil's answer, we can hear Phil's answer to this also. But it's really very difficult because there is no uniform disk evolution. You may have a dead zone where it's magnetically inactive, so there's no accretion there, so matter would pile up outside of the dead zone, and then suddenly the dead zone would become active again, so you have a burst of material there, or planet forms there, planet is piling up at the edge of the dead zone, and then it tries to move into the dead zone, so it can heat up the dead zone, it can become active again, so you can have very complicated evolutions. You can imagine arbitrarily complicated evolutions, in fact. So this is beyond the scope, I think, of this lecture. You just have to keep in mind that if you plug in, I think, a constant alpha, which I think is one of the parameters you can vary, you can make different disk models here with it. You assume you have a constant alpha throughout with radius, I think, yeah, constant alpha, whatever, or you can vary this. Then you can make disk models and you can see how crucial this parameter is. So this will give you some handle to see how important the evolution of the disk is. And then, of course, you have all these other little things here. Yeah.